Welcome back to another lesson on logarithms. Last time we saw how to multiply using logarithms. We are going to revisit that idea today, including some historical perspective on how generations of scientists and mathematicians used to perform multiplications without an electronic calculator. From last time, we observed these patterns. For better clarity, I have extended the table of numbers. Notice as we shift the decimal from 2.3 to 23 to 230 and so on, there is no change in the mantissa, the blue digits to the right of the decimal. The only change is the characteristic, seen in red, which increments by an integer each time. The same thing can be said for 4.7, 47, and so on. This means we don't have to recompute the logarithm each time. We can adjust the characteristic and leave the mantissa alone. Consider the representation in scientific notation. 2,300, for example, is 2.3 times 10 to the third power, as seen in the fourth row. Notice the characteristic of each logarithm is the power of 10 in scientific notation. I've used color coordination to guide your eyes. Perhaps it is best that I stop rambling and let you visually digest this. Pause the video as long as you need to do so. To fully demonstrate why that pattern exists, we are going to use the laws of logarithms boxed in red. Consider the case for 2,300. In scientific notation, that is 2.3 times 10 to the third power. The 3 comes out front, and the base 10 logarithm of 10 is 1 by definition. So we are simply adding an integer, 3 in this particular case, to the left of the decimal. Very simple. It might look different at first glance, but the same rule applies to negative powers of 10. In the case of negative 1, we simply subtract 1 from the log of 2.3. That is approximately negative 0.638. Looking at the blue mantissa, there seems to be a jump between the first two rows on this table. However, after that the mantissa is the same all the way down. Even when the argument is less than 1, the same rule of adjusting the characteristic applies. We simply subtract 1 each time we move the decimal leftward. Because we use a base 10 number system and the natural log is base e, the pattern is not so simple for the natural logarithm. Using the scientific notation approach, it is evident that each time you move the decimal, you are either adding or subtracting an integer multiple of the natural log of 10. This corresponds to k positive or k negative. We have computed the natural log of 10 to be approximately 2.3 in a separate lesson, but this can be easily verified using a built-in function on a scientific calculator. So now it is time to look at log tables. These were used in days before electronic calculators because they greatly reduced the burden of multiplying numbers by hand. Electronic calculators are incredibly useful and have done wonders in our modern age. Nevertheless, it is still important to remember our history, and here it is my attempt to give you a taste of appreciation for the past, which laid the foundation for our present era. Here we see 1,800 entries. They represent the base 10 logarithm of every 4-digit number between 1 and 10. That's because after 10, the pattern repeats itself with only a shift in the decimal position. They are accurate to 4 digits. It may seem overwhelming at first glance, but just wait. I will show you how to read this table using a couple examples. Suppose you wanted to know the common log of 1.863. You would find the two numbers boxed in dark red and add them together. Why is this? 1.863 equals 1.86 plus 0.003. The entry for 1.86 is 2695. This is actually the mantissa, so we include a decimal in front of it. Because 1.863 is between 0 and 10, the characteristic is 0. We get the 7 from the column corresponding to 0.003. It actually means 0.0007, but historically was written otherwise to save space and probably ink too. Adding them up gives us the number boxed in green. Compare that to the answer given by the built-in function on a scientific calculator, accurate to 4 digits. Now let's return to this multiplication problem. In the last lesson we computed logarithms. Today I'm going to show you how to use a log table to get the same result. Here it is at a glance. Hold on a moment and I will zoom in on the details with an explanation. For 23 and 47, we pulled the logarithms shown on the left-hand side. Their sum equals 3.0338. We only care about the mantissa for now, which is underlined in orange. 0338 can be broken into 0334 plus 0004. Why did I do that? You'll see in a moment that these correspond to table entries. 0338 itself is not on the table. From the table, these entries correspond to 1.08 and 0.001. 1.08 plus 0.001 is 1.081. Now we can look at the characteristic in red. This is 3, so move the decimal 3 places to the right. Of course, we know that the product of 23 and 47 is 1081. By moving the decimal, that's exactly what we got. This is boxed in green. So here is the common log of 4.7. Since we have to move the decimal rightward one time to get 47, the characteristic is 1. So from here we know that the log of 47 is 1.6721. Same idea for the log of 23 boxed in blue. We just saw a few slides back that 1.3617 plus 1.6721 is 3.0338. We only care about the mantissa, 0338. In orange, we see a 0334 plus 4. This corresponds to 1.08 plus 0.001, as seen in purple. That is 1.081. Now we care about the characteristic, which is 3. Move the decimal 3 places to the right. The answer is 1081. Wow! We just used log tables to multiply two numbers together. Go ahead and practice a few examples for yourself. You can find log tables similar to this one in some old textbooks or by searching online. While log tables saved much computation time over the centuries in which they were used, the first ones took decades just to produce. In the upcoming lessons, we will explore the construction of log tables. If you have any questions, feel free to ask them in the comments section below. Also, don't forget to like, subscribe, and share this video with a friend. I appreciate your support and look forward to seeing you again.